Hello! We introduced Nash equilibrium for mixed strategies last time. In this lecture, we will discuss support characterization, which is a tool that can help with determining what the best response function looks like. This will involve some linear programming. Recall that the best response function maximizes a player's utility, which is ui of x, which is this expression here. For each pure strategy S for player I, we multiply the probability that S is selected by the utility of playing S as a pure strategy, and we sum over all possible S. Now suppose that X bar minus I is a fixed strategy profile for the other players. The goal of the best response function is that given this profile, which mixed strategies xi for player I maximizes the utility? We can write this problem as a linear program as follows. We maximize the utility subject to the sum of all the entries in xi is 1 and xi is non-negative. We let P be this linear program. Here, the variables are xsi for each of the strategies S for player I. Now that we have a linear program, naturally we want to know what is the dual. Here, there is only one constraint, so there is only one dual variable, y. In the dual, we are minimizing y. For each variable in the primal, there is a corresponding constraint in the dual. Each variable xsi shows up once in the constraint of P with coefficient 1. So we also have y with coefficient 1 in the constraints for the dual. And this is greater than or equal to the coefficient of xsi in the objective in the primal, which is the utility of playing S for player I. And we will call the dual D. First note that both of these linear programs are feasible. Can you see why? Well, P is feasible because we can set xi to be any probability distribution and it would be a feasible solution. And D is feasible because we can set y to be the max value of all the possible utilities, and y will be greater than or equal to all such utilities. Therefore, both P and D have optimal solutions, and their optimal values are equal. Now the dual D is easy to solve. The optimal solution to D is y is equal to the max over all strategies of I, ui of S x bar minus I. This is the maximum utility when pure strategies are played against x bar minus I. So this means that P also has optimal value y. Recall that P is trying to maximize the utilities over all possible mixed strategies for player I. So the maximum utility of all the mixed strategies is equal to the maximum utility of all the pure strategies. Now let's look at another one of your favorite things from linear programming, which are the complementary slackness conditions. So, what are the complementary slackness conditions here? The CS conditions are xsi is equal to 0 or y is equal to ui of S x bar minus I for all the strategies S for player I. Equivalently, this means that xsi is greater than 0 implies y is equal to ui of S x bar minus I. Translation of this is that only pure strategies with maximum utility could have positive probabilities in the best response. Or, Pure strategies that do not have maximum utility will have probability 0 assigned to it. Recall that the complementary slackness theorem says that a feasible solution is optimal if and only if the complementary slackness conditions hold, and being optimal means that we have the best response. So that gives us the following theorem, which is the support characterization theorem. Given a fixed strategy for the other players x bar minus I, a mixed strategy xi is in the best response function for player I if and only if xsi greater than 0 implies that S is a pure strategy of maximum utility against x bar minus I. There is a definition related to this. For a mixed strategy xi, the support is the set of strategies with positive probability in xi. So we can now rephrase support characterization as follows. Xi is in the best response function if and only if the support of Xi are strategies with maximum utility. We now go back to the Bach or Stravinsky example. Suppose player 2 plays x2, which is q1 minus q. The utilities of player 1 using pure strategies are as follows. The utility for playing Bach is 2q, and the utility of playing Stravinsky is 1 minus q. Depending on the value of q, the strategies with maximum utility are different. In the first case, suppose we want Stravinsky to have a higher utility than Bach. That means that 2q is less than 1 minus q, meaning q is less than 1/3. Since playing Bach has lower utility than playing Stravinsky, Bach is not in the support and will get probability 0. So in the best response function, we have only one element, which is 0, 1. In the second case, suppose we want both options to have the same utility, so 2q is equal to 1 minus q. That means that q is equal to 1/3. This means that both Bach and Stravinsky can be in the support, and both of their probabilities can be non-zero. This means that any combination works and will satisfy the support characterization theorem. So the best response function will include all possible probability distributions between these two strategies. In the last case, suppose we want playing Bach to have a higher utility than playing Stravinsky. So we have q is greater than 1/3, and Stravinsky is not in the support. So the best response function has only one element, 1, 0. And this matches the best response function we calculated in the last lecture. For our next example, let's consider a two-player game with this payoff table. Suppose that player 2 plays the strategy x2 is equal to 0, 1/3, and 2/3. So what is the best response for player 1? We first calculate the expected utility for each pure strategies for player 1. When player 1 plays A, the expected utility is 5/3. When player 1 plays B, the expected utility is 4/3. And when player 1 plays C, the expected utility is 5/3. So we see that playing A and C will give us the maximum possible utility among the pure strategies. And because B is not among the maximum, by the support characterization, we must assign probability 0 to B. And any distribution over A and C will work. So the best response function for player 1 is P 0, 1 minus P, for any p from 0 to 1. As an illustration, we can calculate the maximum utility for player 1 over all the possible mixed strategies, which is p times 5/3 plus 1 minus p times 5/3, which is 5/3. and this is equal to the maximum utility for a pure strategy. Now, any strategy in the best response function for player 1 maximizes the utility for player 1. But which of these maximizes the utility for player 2? We need this to give us a Nash equilibrium. So let's make this calculation. Suppose player 1 plays x1, which is p, 0, 1 minus p, which is in the best response. We can calculate the utilities for player 2. The utility for playing D is 4 minus 2p. The utility for playing E is 1 plus 2p. And the utility for playing F is 7 minus 6p. So if x2, which is 0, 1/3, 2/3, is in the best response, then E and F must have maximum utility. In particular, they must have the same utility. So 1 plus 2p is equal to 7 minus 6p. So p is equal to 3/4. We can calculate the utility for E and F to be 5/2. The utility for D is also 5/2, so indeed E and F do have maximum utility. And so does D, but this is fine. D has probability 0, so it could be in the maximum or not. So the x1 and x2 we have are in the best responses for each other, and together they form a Nash equilibrium. So one possible algorithm for finding Nash equilibrium is by looking at possible combinations of the supports for each player. In our example above, suppose we were not given x2, and instead we ask, suppose the support for P1 is A and C, and the support for P2 is E and F, then we can use support characterization to find a Nash equilibrium or prove that none exists for these supports. The problem is, there are exponentially many support sets for each player, roughly 2 to the k if there are k pure strategies. So this is not a practical method. But you can still use this to solve this exercise. Show that in the game of rock, paper, scissors, both players playing 1/3, 1/3, 1/3 is the only Nash equilibrium. And that concludes our discussion on support characterization. In the next lecture, we will look at a mixed strategy problem with more than 2 players in the voting game.